Hello, AP Bio people. Welcome. This is Miss Wythe coming at you for fats, a little bit of information about fats, also known as lipids. So I'm going to share my screen with you and show you my notes that I'm working with in OneNote. So we've already got carbohydrates taken care of. So there's a video there. That was probably longer than this one's going to be. Got our carbohydrate pieces, carbohydrates. Here we go for fats. I'm gonna make it, just going to move this over. If you would like to change colors, that's what I would recommend. If you're changing topics or molecules, maybe change colors of your notes. Visually, what color do you picture when you think of fats? Maybe use a highlighter for some of the terms within this section. Any of those visual cues might be really helpful. There are two images associated with this section. There's this one here with butter and olive oil, and then there's also here the structure and examples of 3 types of fats. So, excuse me. Late night recording. So the atoms that are present in our fat or lipid molecules is again carbon, hydrogen, and oxygen, but the structural difference of them to distinguish them away from sugars is that in fats we're going to be forming chains with these carbons and hydrogens, where in sugars we were forming rings with carbon, hydrogen, and OH or oxygen off on the sides. So for fats, the subunit piece, there's 2 this time, so a little bit of variety. The glycerol is a really very polar molecule, also known as the head of the fat molecule. It's where the other pieces are connected to. And it has oxygen atoms as part of it, so that's sort of what makes it polar. The other piece, sorry, of the fat molecules are fatty acid chains. So fatty acid chains are the portion of a fat molecule that is really, really non-polar. Fatty acid chains are predominantly all carbons connected to other carbons with hydrogens coming off of them. Very little to no oxygen unless it's all the way at the one end of the fatty acid chain where it connects to the glycerol. So in the model here, this image of the butter, you've got 3 chains. I'm recording, Mr. Rivers, you can come back. 3 chains of the fatty acids are connected to the glycerol, and you can see they're all very, very straight, and that's showing single bonds between all of the carbons with a saturated, filled in all the hydrogen atoms that you possibly could get. This one here of olive oil, it's showing some double bond action happening. So when you are going to form a double bond between carbons, you have to have less hydrogen available, because if we're going to put more bonds between the carbons, you got to remove some of the hydrogen atoms to do that, to have more bond numbers between carbon atoms. So when that occurs, the chain of hydrocarbons gets a kink or a bend in it where the double bond was. So glycerol doesn't have a lot of variety to it, but the fatty acid chains do have variety. There are 2 categories of them. We have both saturated fat, like I mentioned, and unsaturated fat. So the saturated fat is, in a sense, saturated with the maximum number of atoms possible in that fatty acid chain. All single bonds pack in as much matter as you can, and therefore in our model or a drawing of fat, the chains, the fatty acid chains in the drawing, are drawn very straight. And if they are very straight, we can pack them together very tightly. And that tends to result in fats that are solid at room temperature. Oh, excuse me. It tends to be our animal fats like butter, bacon grease when it cools down, things like that, that are sources from animals. The unsaturated fats end up having those double or triple bonds. The chain of fatty acids gets a bend or a kink in it, and because the chains are all bendy and kinky, they're taking up a lot more space. They're not as densely able to be packed as tightly. So you can see in the same like 1 inch of my notebook, I was able to fit 5 saturated fats side by side, we're in the same amount of space of unsaturated fats that can only fit 4. So the unsaturated fats are less dense overall. At room temperature, they are liquid. So that is things that are like olive oil, peanut oil, canola oil, vegetable oil. These are the fats that are coming from plants. Plant fats tend to be the unsaturated fats that are available. So that's a little bit of variety within the subunit category of fats. But again, the glycerol is the same. You are getting different polymers based on how many of these subunit pieces you're connecting. The length of the fatty acid chains is also a little bit variable, but that's not critical for the purposes of this class. So let's look at the 3 polymers and their uses that we get from fats. We have triglycerides, phospholipids, and steroids. I'm going to go ahead and do some drawing here too. Oops, we got 1. No, weird line. Phospholipids and steroids. Here it says sterols, but I'm fine with steroids. It's a little more common nomenclature. So the triglyceride structure, you can see that we've really abbreviated and not drawn in every single atom here, but you've got the glycerol head, 3 fatty acid chains. So I don't know why I'm trying to reinvent the wheel. 3. Oh, I want to draw with touch. There. 3 fatty acid chains on the triglyceride. They can be saturated, unsaturated, trans fats. Trans fats are modified chemically to, basically it is like an unsaturated fat, but we pack in the more hydrogen to basically saturate it. It's trans fats are not so great. They're chemically modified and your body kind of goes like, what is this? This is not from nature. Not a big thing that we need to focus on for this unit either. But our butters and oils, stored fat in an animal, that's all triglycerides, fat cells, if you will. Phospholipids, alternatively, I should say triglycerides, similar to how glycerol, wrong word, glycogen, excuse me, similar to how glycogen is the carbohydrate storage molecule short term for an organism like an animal, triglycerides, or the fat molecule, is the long-term storage, in the sense that, hey, it is a time of plenty, you can eat and consume food, your body will convert that into fat to hold onto for a long period of time when one day there might be famine and not as much available food, and then you have that resource stored for yourself. So that is, again, triglycerides, 3 fatty acids attached to the glycerol. The phospholipid, this one is drawn a little bit differently. So it again has the head molecule, which is glycerol, but here it says phosphate head. It's because it's within the glycerol, there is a phosphate group attached in there, and then it has only 2 fatty acid chains connected. This is also the molecule that forms lipid cell membranes of all the cells. So that's why I drew them here. There we go. It's hard to see my pen in the dark. I drew all of these as phospholipids. They all have 2 chains instead of 3. So the phospholipids needed literally for every cell on the planet. Every cell has a membrane of phospholipids around it. It is a bi-layer. It's actually 2 sets of phospholipids sort of facing each other, tails to tails. We will have a further unit on this about cell membrane and its structure coming up soon. The last group for fats, the sterols, or steroids as I'm going to call them, they look like this. Very different than the triglycerides or the phospholipids. It's not a glycerol head, it's not fatty acid chains, it's almost like this weird total other like black sheep of the family in this case. But if you look at the representation of this steroid molecule, you see no oxygen on it except for here at the end. There is an OH hydroxyl group on one end of the molecule. Everything else, all the letters are eliminated. It is assumed then that everything else is basically carbons. So the steroids all share a 4-ring structure. So we've got 1, 2, 3, 4 right there. and then a little bit extra chain of carbon on the side. But the unique part is that it's still got this polar OH side chain hanging off the side. So behaviorally, steroids fall into the group of fats, even though structurally they aren't shaped in the same way or with the same subunits. So they all have this 4-ring, all carbon structure with a side chain. Various steroids that fall into this category is cholesterol, which we're going to talk about again in our structure of the cell membrane coming up in another unit. You could get into the estrogen, testosterone, progesterone, all of the hormones that are actually what we call fat soluble. So these are fats. Fat doesn't dissolve into water because they are very unalike. And so where are your hormones getting stored? In your fat cells, and because they are alike and similar to fat. So just something kind of neat with that. But there are a lot of varieties within the steroids. But we will get more into them if we have like examples specifically of like hormone information, stimulus, and how your body responds. So fats is pretty simple. We've got those 2 subunits, how you connect them, and varieties amongst them that make our 3 different major fat polymers, the triglycerides, phospholipids, and steroids, or group of steroids. In general, fat polymers, very nonpolar for the most part. If I were to highlight on this molecule, the one here of the butter, all of this is nonpolar, all of this is nonpolar, all of this is nonpolar. It's just the, oopsie, other color, the glycerol head right here that is polar. So in terms of proportion of the molecule, the majority of it is nonpolar with just carbons and hydrogens that don't like the water. And the glycerol head is the polar part because it has the water and it is willing to interact with water. So this structure of the molecule will come into play as to why the cell membrane is structured the way that it is. But overall, most of fats are non-water soluble and non-polar. Right? So that's the tidbits about fats. Thanks for playing. Bye-bye.